Okay, so thank you everyone for being patient and waiting. And let me start with something that I almost never get a chance to say, which is, hi, Mom and Dad. And thank you for everything. And you now get a chance to see what I've been doing all these years. So today I'm going to be discussing Einstein's discovery of general relativity, which, as I mentioned, is something that we're celebrating the 100th anniversary of this year. And today's talk is going to be about the path he took to developing that theory. And there are several things that are striking about this path to a new theory that I think makes Einstein interesting from the point of view of philosophy. So first of all, as I'll describe briefly tonight, it was a very rough and winding road that he took over about 8 years of trying to sort out the ideas that he would need for a new theory of gravity. And one thing that's characteristic of the way he approached these problems is that he had a kind of philosophical assessment of the basic concepts of physical theories. And this will, I'll emphasize a few points where he's really focusing on what are the concepts that are really needed for a given physical theory to be successful. And he's very perceptive in his critical assessment of existing physical theories, which allows him to be imaginative and creative in coming up with solutions to the problems he's facing in developing a new theory of gravity. So just a blanket acknowledgement at the start, much of what I'm talking about today is a reflection on the work done by other people, historians and philosophers. So there's been a real, in the last about 20 years, partly because of the Einstein Papers project, which is a large project devoted to publishing all of Einstein's work with commentary on what he was doing and so on. There have been a lot of scholars involved in the Einstein Papers project who have unearthed the details of the history, which I'm giving you a synopsis of tonight. So there's a lot of them. I'm just going to mention one source that is a kind of detailed overview that summarizes much of the results of these earlier discussions, and that's a paper by Michel Janssen, which is a detailed discussion of Einstein's struggles from 1907 to 1920, which is in a book that appeared recently called The Cambridge Companion to Einstein. So if this is a topic that excites your interest, that's probably one of the best things to look at, which has a sort of summary of recent scholarly work in this area. So I'm drawing on the work of a lot of other people, and I'm not going to be pointing out in every place as I go through what the individual contributions were. So let's now look at what Einstein did. So first of all, general relativity, what is it? It's a theory of gravity. So ultimately, Einstein, 100 years ago, created an alternative to Newton's theory of gravity. But how he got there is like a play in 2 acts. So the first act, which I'm going to focus on, was his theory of special relativity. This was something he introduced in 1905. And I'm going to describe how he developed these ideas. This is the source of a lot of the ideas that you've heard about, such as the twin paradox, the idea that space and time are different than you might have conceived of them. I'm going to focus on what happened with the development of special relativity, partly because it provides the first act in the development of Einstein's views about a theory of gravity and general relativity. So the first act, the first part of the talk, I'll focus on special relativity, and then I'll shift to what Einstein took up shortly after his success in 1905. So around 1907, Einstein began focusing on the next step, which he always thought of as a generalization of this earlier theory. And he's the one who introduced the name general relativity. It was meant to be a step beyond what he'd done in 1905. And so I'll focus on the concepts that he used in guiding his way to this new theory, and the troubles he experienced in employing those concepts. And finally, like any good play, this has a dramatic conclusion. It turns out that as he was nearing completion of the theory, he ended up being involved in a race with the most preeminent mathematician of his day. And so the last month of work that he put in was probably the most intense period of work in his life. That's what he reported to his colleagues. So I'll conclude with the race for the prize and then talk about some overall concluding comments briefly. So let me dive right in to talking about special relativity. So this might be unfamiliar territory, but I'll try to explain things so that you can see what's so striking about this theory. So this was at the start of Einstein's paper in 1905. He characterized special relativity as a theory that was the consequences of two postulates. So Einstein was very much a fan of formulating theories in terms of clear postulates which state the basic concepts of a theory so that you can understand what follows from them and the consequences that come from those postulates. So these are meant to capture the core ideas of the theory of relativity. The first is a principal relativity, and the second is the light postulate. I'll say more about the principle of relativity in just a moment. That's how he characterized it in the paper in 1905. The light postulate is the claim that light always propagates in empty space with a definite velocity, independent of the state of motion of the emitting body. So this is an idea that follows from earlier work by physicists to understand how light works by Maxwell and others. And the first is a characterization of a principle that's quite fundamental in mechanics. And it goes back to Galileo. Now, the striking thing is that these two seem to be incompatible on the face of them. And I want to explain why they seem to be at odds with each other, even though Einstein starts off stating them as two postulates. So let me say a little bit more about the principle of relativity then to start. So the principle of relativity, as I've formulated it in a slightly simpler way than Einstein did here, claims that all observers in inertial motion see the same laws of physics. So first let me say what inertial motion means. It means that you're moving uniformly at constant speed with no rotation. So no acceleration of any sort. So the kind of example that Galileo used in the 17th century was, imagine that you're under the decks of a ship sailing on very smooth seas. I don't know about you, but I've very rarely been on a ship that is moving inertially. It's maybe more plausible for us to think of a plane, that if you're on a plane and it's moving, imagine that you've fallen asleep on a plane and you wake up. Sometimes it's hard to tell whether you've actually already taken off or in flight or are still sitting on the runway. That's a reflection of the fact that even if the plane is moving at at a constant velocity, everything within the plane will obey the same rules. It will look the same way. So when the waiter pours you a drink, when you're on the plane, you don't have to hold your cup sideways to catch the liquid. It obeys the same rules as everything does if the plane is at rest. So in that sense then, if you're in uniform motion, you will see the same laws of physics, and you won't actually be able to distinguish whether you're in a state of rest or in a state of uniform motion. Now, the conflict between this, or the apparent conflict between this and the light postulate, follows from some odd things about light. So now just think about a standard situation where you are asking what the apparent speed of something is. Now, if I have a gun or a champagne bottle and the cork is shooting out of it, and I'm standing here and I shoot the cork out of the champagne bottle and I ask Stathis how fast it's moving, he'll give me an answer. He'll have an estimate of how fast it's moving. But if I were running along next to the champagne cork, it would look to me like it was going at a different speed. And that's reflected just in the way that we usually add velocities when we're moving. And if I were comparing myself to Stathis, I'd have to take into account that I was moving with respect to him in order to see how to compare those velocities. And so in this illustration, this is just taking into the, so we imagine, say, Alice and, or I guess Alan and Bob here, two people who have that sort of comparison, and the one who's moving has to add in his velocity with respect to Alan in order to figure out what the velocity of the champagne cork is. So this is something that is very commonsensical. It's something you do all the time when you're comparing speeds of things and taking into account your own state of motion. But there's something funny that happens with light. According to the theories of light that were developed in the 19th century, no matter who you ask, if I turn on a flashlight or a light bulb, the light rays emitted by that are emitted with one constant velocity, which all observers agree upon. So unlike the case of the champagne cork, where the two of us disagree about how fast it's going because of our relative motion, in this case, we say the same thing. We say it's moving at the speed of light. And that's something that doesn't, it doesn't matter how fast I'm moving with respect to the other observer, I'll give the same answer. So this is why it seems like there's an apparent conflict between the light postulate, which states that this is the way light behaves, and the relativity postulate, because it seems that light doesn't follow the same kind of rules for velocity addition as other things we experience. So both postulates together, again, if you take both postulates, then you can say that all observers should measure the same speed of light, but the rule for adding velocities that I described before just follows from common ideas about space and time. What is velocity but distance over time, right? So when I ask, why do I add velocities the way I do, it's because of how I'm thinking about space and time. So this conflict between standard ways of thinking about adding velocities together and the invariance of the speed of light means that we need to reconsider then our basic ideas about space and time. That if this conflict arises, we need to reconsider what we mean by space and time. Now, there are a few different ways you could respond then to this apparent conflict. One would be to say, well, maybe we're just wrong about our theory about light. Maybe we made a mistake in describing how light propagates, such that it was wrong to think that it always propagates or moves at the same speed. Einstein actually considered this and ruled it out. He didn't think that this would work. And so what he was left with was the possibility of changing our conception of space and time, these basic concepts that seem so commonsensical that and they seem sort of unshakable. He has to consider, though, changing those and giving a critical assessment of our conventional views about them in order to reconcile these two claims. And so here's a later retrospective account of the insight that he had that allowed him to make this breakthrough. So this is from a lecture in 1922. You have to take it with a grain of salt because this is 17 years later, but he's remembering a moment where he had an insight. And this is, let me just quote the part that's highlighted there. So he'd been confronted by this apparent conflict, and that's what he's describing in the first paragraph. And then he says, my solution actually concerned the concept of time. Namely, time cannot be absolutely defined by itself, and there's an unbreakable connection between time and signal velocity. Using this idea, I could now resolve the great difficulty that I previously felt. After this inspiration, it only took me 5 weeks to complete the paper that we're discussing about special relativity. So what was this key insight about time that he's mentioning here? So the question that Einstein started thinking about was, what do we actually mean operationally when we talk about time assigned to distant events? So we have a clock here. Let's say I wanted to ask about the time in comparison between this clock and a clock in, say, London, England, or anywhere else further away. How is it that we actually talk about time at distant events? So what Einstein recognized is that there's an implicit assumption in the way that we usually think about time with respect to distant events, which is that we imagine that there's somehow an instantaneous signal that allows us to say, so forget about time zones and so on, but just allows us to compare the time at this clock with time at other distant clocks. Right? So that we imagine we could just, snap our fingers and say, everything that's at the same time as me snapping my fingers will now say is 7:22, right? But what signal would be propagating outward from my finger snap to all these distant events? What Einstein realized is that if you think hard about the way we actually synchronize clocks, there's always, it's not always the case. You could use slower signals, but the fastest signal that you send is in fact light signals. And so when I'm synchronizing clocks, it's more like the picture I have on the left. So I imagine my clock here, I'll call that A, and I might have another clock somewhere far away. And when I synchronize the clocks, I send a signal from my clock to the other clock, and then it bounces back. And I say, well, you should say, so if the light signal took 4 seconds to do the full round trip, then I'm going to say, you should have set your clock at 2 seconds after what my clock was initially set at, so that our two clocks are in sync. Okay? Now, the tricky thing is that seems like a fairly natural observation, that when you actually talk about time, you should say, well, how are we synchronizing our clocks? And if we do it with finite signal speeds, then like light, what are the consequences? Well, it turns out that if you follow through this reasoning, you have some really striking conclusions. So it turns out that once you've decided that that's how you're going to synchronize your clocks, and that you're not just going to sort of assume in the back of your mind that there's somehow an instantaneous signal connecting the clocks, if you actually think about synchronizing your clocks using light, you'll discover that observers moving with respect to each other will in fact disagree about things that might have seemed like things they couldn't disagree about. They'll disagree about whether two events like that happen simultaneously or not. So because assigning time to those two events is something that involves assigning time to distant events, and it turns out that if I'm moving with respect to someone who's at rest, I'll assign time to different events in a different ordering for some types of events. And also, we'll end up disagreeing about the spatial distance between two events. So it turns out that what we agree on is this weird combined quantity that includes a spatial distance and an amount of time elapsed. All observers will agree on the space-time distance between those two events, but we'll break it up differently into a spatial distance and a time elapsed. So I know that went very quickly. This is one of these things that's quite puzzling and hard to get your head around. But since this is only Act 1, I'm going to have to move relatively quickly over this. I'll be happy to give you some more examples and discussion of this, but this is one of the things that Einstein realized in 1905 was that if you define time in this way, there are all these apparently paradoxical consequences, which are in fact not paradoxical at all. So it turns out that the new conceptions of space and time, where you say spatial distance and temporal distance are observer dependent, how is that compatible with our ordinary experience? Well, this is just a case where the conventional wisdom we had about space and time can be treated as a kind of useful approximation. So given that everything we routinely experience in ordinary life moves really slowly with respect to the velocity of light, we don't often notice disagreements about elapsed time between two events or disagreements about the distance between two events. So we can recover what was valid in our ordinary experience as just a kind of approximation to these new ideas. And this is what I mean when I say that Einstein realized there's nothing deeply paradoxical here, perhaps counterintuitive, but nothing actually paradoxical. But again, there's a kind of destructive aspect of his analysis of our ordinary concepts of space and time. They're actually based on something that doesn't mesh with what we're in fact doing. The assumption that we can talk about time of distant events unproblematically assumes that we're kind of linking things up with an instantaneous signal. And in fact, we never do that. So the traditional concepts we have of space and time are in some sense deeply misleading, even though they can be used as a kind of approximation to this more accurate picture that Einstein has introduced. So these concepts are compatible with our ordinary experience, but there's a strong case for saying that this is the more correct picture of the judgments we actually make about space and time when we're pressed to do so in a precise way. But what about other theories? So Einstein in 1905 has said, well, look, we need to revolutionize our conceptions of space and time. And he's argued that it's not actually paradoxical, that you can do this in a way that's consistent. But what about other parts of physics, given that other parts of physics were all formulated using what were then current ideas about space and time? And the theory of gravity is particularly clear that this is really obviously going to be a problem. So just think about, when you learn Newtonian gravity, whenever it was that you studied it last. What is the force of gravity? Well, it's a force of attraction. So imagine you have two bodies at some distance. It's a force of attraction that depends upon how far apart they are, and it acts instantaneously between them. It's an instantaneous force of attraction that depends on their distance. Well, even just in stating it that way, you should have heard, if you thought about the sort of new ideas of special relativity, your ear should have pricked up at 2 points. What do you mean by distance? And what do you mean by at the same time? So special relativity says, look, both of those concepts are observer dependent. So Stathis and I, if we were trying to measure the force between two bodies, if I were moving with respect to him, I'd say, no, they're a different distance apart than what you estimated. And I'd have a different view about what time it is that the interaction is occurring. So obviously there's an issue about Newtonian gravity and how it's going to be reformulated in light of this changing conception of space and time. It's built on assumptions that are no longer something that you think are valid. Okay? So this is something that Einstein came face to face with in 1907, where he first said, well, if my new ideas about space and time are correct, we're going to have to reformulate some of the most successful theories of physics, including Newton's theory of gravity. Okay, is everybody with me in seeing what the problem is? You no longer have an observer-independent notion of space and time, but Newton's theory assumes that you do. So how are you going to respond to that? So Einstein characterizes this as a rough and winding road from around 1907 down to 1915, when he successfully introduces the theory of general relativity, is in 8 years in which he struggled to figure out how to formulate a new theory of gravity. So he's recognized that in light of special relativity, you need a new theory of gravity. And it took Einstein a long time to see how to resolve this problem. And it's shortly after this, by the way, in 1919, when Einstein becomes an international celebrity. So 1919 is the year that there's an eclipse expedition headed up by Eddington and some other astronomers, which confirms some of the most striking predictions of general relativity. And that's when he starts appearing. So this is a magazine that was published in 1919 in Berlin. This is when he starts appearing on the cover of magazines, and he's continued to do so ever since. But this is shortly after he discovers it, it's given this fabulous test. But I'm going to be focusing mainly on what happened in these 8 years leading up to 1915. So in these years, the way that Einstein characterized the question was that he was trying to generalize relativity. So he'd had this amazing success in 1905, but he thought he had to take a further step in order to solve the problem of gravity. And during this time, he introduced several ideas, guiding ideas that were things that he was using to help him formulate this new theory, principles that he thought the new theory should satisfy. There was also a lot of new mathematics. So it was during this time that, now I'm forgetting the exact quote, but he says something to the effect that whatever your problems are in mathematics, I can assure you mine are greater still. There's a famous quote of him to that effect. This is during a time when he was trying to learn how to describe geometry of curved spacetimes, and it involved a lot of very challenging mathematics. I'm not going to say a lot about that, but that's something that also occurred during this period. And then there are various problems that he faced in analyzing the new theory. I'm also going to say less about those specific problems. I'm going to focus on these heuristic principles that he used to guide the search for the new theory. So we have this conflict between special relativity and the theory of gravity. Now, if you aren't Einstein and you're a physicist around at that time, there's actually a fairly straightforward way of responding to this, which a lot of his contemporaries, these are some of the more famous physicists of the period, although there are no Einsteins, right? And you probably haven't heard of them. But all of these people considered the question of how to formulate a theory of gravity that's consistent with the ideas of relativity. And they made some fairly straightforward moves to try to formulate such a new theory. So in some sense, there's an incompatibility, but there's a fairly natural way to formulate gravity such that you replace the spatial and temporal distance with the combined space-time distance. That wasn't Einstein's response. So these guys thought of it as, okay, this is a fairly straightforward project of rewriting Newtonian gravity. Einstein's response was quite strikingly different. He thought that the conflict between special relativity and Newtonian gravity that I've formulated really just reflects that there are much deeper problems here. And in particular, he thought that there were challenges to the basic concepts of Newtonian physics, the idea of inertia. So again, the principle of inertia is the idea that an object will remain in its state of motion unless there's some force acting on it to change that state of motion. So he thought that there was a connection between that concept, which is a fundamental part of Newtonian physics, and the force of gravity. And so he pursued a much more challenging route to try to formulate a new theory of gravity. So I'm going to try to characterize this conflict in a bit more detail, rather than just saying that the problem arises in a force law that includes distance and time. So another insight due to Galileo is a discussion of free fall of bodies. So imagine, so this is a picture that's meant to illustrate shooting 3 different, say, billiard balls off the edge of a table. And you line them up and you hit them with different speeds. You hit one to go much faster, one to go slower, and one in the middle. And you ask, how long do they take to fall? So when do these balls hit the floor after they've been shot off the edge of the table? Now, Galileo's treatment implies that the time of fall, they're all falling due to gravity, will be the same regardless of how hard you've hit them, right? So even the one that's going much faster, the time for it to fall through that vertical distance is the same as that of the other bodies. And this isn't just dependent on their horizontal velocity, how fast you hit them. It also doesn't matter what their composition is. So regardless of what they're made, they will fall in the same way as long as you don't have to worry about effects like air resistance, right? So this is sometimes called the uniqueness of free fall, this idea. And as I said, it goes back to Galileo. But it actually conflicts with special relativity. So now imagine, again, that we've set up the experiment and Stathis is observing it so that he can see these balls falling at the same time and hitting the ground. But if I'm moving with respect to him, according to special relativity, I will not agree with his judgments of what events are simultaneous with each other. I will actually think that those balls land at different times. They can't all land at the same time. Okay, so this reflects a problem. One possible conclusion would be say, well, Galileo's idea about how bodies go through free fall was wrong. Maybe special relativity has shown that Galileo was in fact wrong. So again, here's the conservative response. This idea of Galileo's was wrong. Special relativity, Einstein's theory in 1905, was in fact correct. And you might make the case, for example, that this might be, so there's a lot of evidence that Galileo's idea is on the right track. So to defend this line of view, you'd have to say, well, the differences in the speed or the time of free fall are very small. So maybe you could recover the idea that Galileo's claim only holds approximately, so it's compatible with all the evidence you see. But you'd still have to say it is in fact wrong to think that bodies fall in the same time. So Einstein took the opposite approach. He thought that Galileo's idea, his treatment of the uniqueness of free fall trajectories, was in fact correct, and it was a deep insight. And so in 1907, he's ready to throw out the theory that he himself proposed in 1905 because he thinks you need to preserve this insight of Galileo's. Right, so this is quite striking to me that he was ready to modify special relativity, where a lot of his other contemporaries were considering alternatives in which you instead reject Galileo's treatment of free fall. So, and this is what Einstein started talking about in 1907 as an attempt to extend relativity and to develop a new theory. So let me say a little bit about the questions he was posing here. So remember, one of his postulates in the first paper of 1905 was the claim that all observers in inertial motion see the same laws of physics. So what Einstein posed, the questions Einstein posed in 1907 were, does an extended version of this principle apply or hold for accelerated observers? So can we loosen the restriction to inertial observers in our initial formulation? If we start talking about accelerated observers, we'd have a more general version of the principle. And he thought that extending the principle in this way could help us to understand the problem with gravity that we started with. So sorry, this is slightly different. I've filled in what inertial motion means in this formulation. And here's one example of a principle of general relativity. All observers in any state of motion see the same laws of physics. Sometimes being too general is not a good thing, and this actually seems quite problematic. So if I'm actually on a rotating table, say, and I'm trying to describe the motions of bodies, it isn't the case that being on that rotating table, things move in the same way as they do in other settings. So this formulation is actually too general. So that obviously can't be, you can't just generalize it haphazardly. There has to be something different and more refined in your attempt to generalize the principle of relativity. So Einstein considered, are there other cases where observers in different situations see the same laws? So are there analogs of the case that we imagined where you're on the tarmac in the airplane or up in the air in the airplane? And we said that you would see the same laws being effective in those two settings. And so this is a case where you've probably heard of Einstein's elevator thought experiment. This is something he called at one point the happiest thought of my life. And the thought he had was that there might be a kind of equivalence between a case of being at rest in a gravitational field and accelerating, namely falling freely in the same gravitational field. So his idea was that so the way he put it initially was slightly different. Imagine that you're in an elevator that's enclosed, and we do the same kind of thought experiment we had with the airplane. So if you're in the elevator and it's accelerating, you'll notice that if you let something go, it will drop towards the floor of the elevator. He's imagining that you wouldn't actually be able to tell the difference between two cases. One is that the elevator is just a box that's sitting on the surface of the Earth, and the reason the thing drops when you let it go is just gravity pulling the whatever it was down to the bottom of the elevator. A different effect would be if something is pulling the elevator through space and accelerating it, and that should lead to the same effects in terms of the motion of objects internal to the box. So here he's thinking that similarly, if you're in free fall, actually all the objects around you will be accelerating in the same way. Similarly, if you're at rest in the Earth's gravitational field, everything will be feeling an acceleration. So this is a similar thought experiment to the elevator. And here we now imagine the roles reversed, right? So here we have Einstein, rather than in a room that's in a gravitational field, it's accelerating, and the spaceman is now not in free fall, but he's at rest outside. So the question then is, can we think of these as similarly linked situations where we have a kind of symmetry in terms of what observers see? So now thinking in terms of relativity extended to acceleration, in these cases, either observer can claim to be at rest. What they'll disagree about is whether there's a gravitational field present that's causing acceleration. And so the two cases can either be accounted for with a gravitational field or with acceleration. So this motivates the idea that gravity and acceleration are linked, and we can have an exchange in describing a physical situation in terms of one versus the other. Now, the way that Einstein formulated this as a guiding principle in his search for a new theory was to say that a freely falling frame is in some sense equivalent to an inertial frame. And so the way that, so a different way of stating the same insight, although I probably haven't said enough to explain how this leads to a linkage between inertia and gravity, is that we should, in order to make this claim linking gravity and acceleration, what Einstein's doing is really treating inertia, the tendency of a body to stay in a state of motion, and the force of gravity as two aspects of one and the same thing, right? So he's thinking of them as essentially linked. And he at one point says that they have a unity of essence, that inertia and gravity he regards as really just one sort of two sides of one coin. And this thought experiment involving the elevators is motivating that linkage because of the linkage between acceleration and gravity. Okay, so there's another concept that's important that was guiding Einstein's search for the theory, which he called Mach's principle after an Austrian physicist, Ernst Mach. He linked this discussion of the equivalence principle with a way of thinking about space, which he attributed to Newton. And so this is probably something well, we can talk about this more in discussion because there's a bit more backdrop to this particular criticism. But the thought is that when Newton says in the formulation of the laws that a given body will stay in motion unless there's a force acting upon it to change its state of motion, you could ask the question, what is it that determines what that motion is? How does the body know what line to follow in space? Now, I don't, in fact, think that this is the right way of understanding Newton, but this is the way that Mach and Einstein thought of Newton. They thought of him as being committed to the idea that there's some space in which you could conceive of that body moving that determines what the straight lines are. And that's what they think of as a conception of absolute space. And so Einstein thinks that that's the wrong way of thinking about inertia. The wrong way, again, is that there's something out there, absolute space, which is somehow telling the body what the lines are that it should move along if it's moving inertially. Einstein thinks it's problematic to have that appeal to absolute space. He describes it at one point as kind of a ghostly entity. How could it be telling bodies how to move? He thinks instead we should describe the effects of inertia as a result of interaction with other bodies, so that you don't have some other thing, absolute space, that's determining how objects should move. It's all just a claim about how bodies interact among each other or with each other. So again, this is something that I can say a little bit more about in questions if there's an interest. But this is a very closely related idea for Einstein, that he thought that Mach's principle and the equivalence principle were closely linked in terms of the heuristics. Oh, actually, sorry, I did have a little bit more. I think I effectively said this already. So this is what I was saying a moment ago. How do we draw the contrast between inertial and non-inertial motion? How do we say when a body is moving in a straight line uniformly, how do we draw that contrast between a body that's being deflected by some force? And Einstein and Mach thought that Newton had to answer this by saying that there's absolute space out there that determines what these straight lines are. And Einstein thought that instead we should define motion with respect to other bodies without an appeal to this conception of background space. So Einstein in 1918, a bit after the main part of the history that we're looking at, formulated this idea as the claim that the gravitational field, the effects of gravity on other matter, should be fully determined by how matter is distributed through space. In other words, it doesn't matter what absolute space you have in the background. It's just a relational property of how matter interacts with other bits of matter. And this is something that he thought was crucial in any successful gravitational theory. Okay, so I've described very briefly, I realize, a few of the guiding principles that Einstein was trying to use to formulate a new theory of gravitation. So these were principles that he formulated in different ways in the period from 1907 up to 1915. There's sort of different phases in his thought as he's trying to formulate these ideas. By 1913, he had a well-developed theory, which is called the Entwurf theory, which just means outline in German. So in 1913, he published a long paper, which is called An Outline of a Theory of the Gravitational Field, which was his attempt to realize all of these principles. And there's a lot of other things going on as well in terms of how he actually mathematically formulated the theory. But, and in the 1913 theory, well, I'll mention this just briefly. The way that these ideas took shape was he argued that in order for a theory to be a generalized theory of relativity, it should have a certain mathematical property called general covariance, which is a feature of how you write down the equations of the theory. Namely, that you don't actually have to write down a specific coordinate system in order to formulate the theory, that it should be a theory that can be formulated in terms of any coordinate system. Now, in 1913, he wrote down this theory. By the summer of 1915, he was very unhappy with the status of the theory. There are all kinds of problems with it. There are problems about whether it fulfilled these ideas of a generalized theory of relativity, and at this period, what that meant for him, is it in fact generally covariant? He was in the middle of arguing sort of back and forth with himself mainly about whether you really should demand that you have a generally covariant theory, and so on. And the other two things I mentioned are problems of a more technical nature about how it is that you actually describe rotating systems in the theory, and also whether you can get something that looks a lot like Newton's theory in the limit. What I mean by that is that Einstein was very much guided by the idea that Newton had given a very successful description of the solar system. So you wanted a theory that got that description back with some small changes, right? So he needed to understand how you could treat this new theory as a generalization of the old theory, but that you recover it as an appropriate approximation. So these are all really serious challenges that he was facing. And I say that there are a lot of storm clouds. In summer of 1915, things were not looking good for the Entwerf theory. He gets an invitation to go to Göttingen in June 1915. So now, during this period, going to Göttingen to give a talk on your theory that that you're sort of happy with but realize has deep problems would be, in contemporary terms, like going to the Perimeter Institute to give a talk about your new theory of quantum gravity, right? So Göttingen was a place where the real experts in mathematical physics of the day lived and worked. And so going to Göttingen was both a terrific opportunity for Einstein to present this theory with all the difficulties he'd been facing with it, and an opportunity for the people in Göttingen to contribute and perhaps pursue the ideas that Einstein had developed and take them the next step. And that's in fact exactly what happened. So David Hilbert was, I think it'd be safe to describe him as the preeminent mathematical physicist of the day in 1915. So he had done work in a wide variety of areas of mathematics, and in the period from 1905 until the point where Einstein went to lecture in Göttingen, was particularly interested in trying to understand the foundations of physics and understand how you could give a formulation of all the different areas of physics in a sort of very concise way. So Einstein was talking to one of the main experts at the time. And it turns out that Einstein's talk inspired David Hilbert to start thinking about gravity as well. And this is, as I said, Einstein at this point was very unsettled about this Entwerf theory. He knew it had problems and he's trying to finish it. And you've got to think about now having the greatest mathematician of the day, in effect, breathing down your neck as you're trying to finish the theory you've been struggling with for 8 years. Okay, so that Einstein at this time 100 years ago was feeling the breath on his neck, right? So he knew that Hilbert was working on this. And this is just a brief selection. There's correspondence back and forth between them that's usually a turnaround time of about 1 day. And remember, this is in the middle of a war. So this is Einstein writing to Hilbert. Hilbert had written him before and was telling him about his own ideas. Einstein writes to Hilbert on November the 18th. The system you furnish, so this is Einstein now comparing his own ideas to Hilbert's. Oh, sorry, one more element I should mention. So Einstein gives a series of 4 talks in November of 1915, which are a series of talks about his theory of gravity. The first one starts by outlining in a very candid way the problems with the Entwerf theory. And in this series of 4 talks, he is very quickly correcting, in effect, in each talk, he corrects some of the problems that he identifies. In the next talk, he throws away what he did in the previous talk, corrects some of the problems, and so on. And so you can see a really rapid progression of his thoughts in these final stages. And so Einstein's writing to Hilbert in the midst of this, and they've been communicating throughout this time. So he writes to Hilbert and says, "The system you furnish agrees. as far as I can see, exactly with what I found in the last few weeks and have presented to the Academy. Today, I am presenting to the Academy a paper in which I derive quantitatively out of general relativity, without any guiding hypothesis, so nothing extra, it's just the theory, the perihelion motion of Mercury. No gravitational theory has achieved this until now. So the perihelion motion of Mercury is one of these cases. I said earlier that you want to recover the Newtonian description of the solar system mostly, right? There are some points where the Newtonian description of the solar system wasn't entirely successful. And the most famous of these was the perihelion motion of Mercury. I mentioned also that some of Einstein's contemporaries had tried to derive gravitational theories that were based on special relativity as well. None of them got anywhere close to predicting the correct amount of this anomalous perihelion motion. Most of them didn't even get the right sign, right? So they had a correction going in the wrong way. So it was actually quite striking that Einstein nailed the amount of the perihelion motion. And as he says, no gravitational theory has achieved this until now. So he's staking a claim here. Look, this is something that now I've done successfully, Hilbert, and let me ensure that I've stated my priority in this. Hilbert's obviously quite impressed. He says, cordial congratulations on conquering perihelion motion. If I could calculate as rapidly as you, in my equations, the electron would have to capitulate and the hydrogen atom would have to produce its note of apology about why it does not radiate. So Hilbert's very impressed with how quickly Einstein was able to perform this calculation. But Hilbert submitted a paper the very next day called The Foundations of Physics, in which he lays out his theory of gravitation. So what we have then in the last months is a series of talks, and the exchange I just quoted from was a week before Einstein's final talk on November 25th, where he presents what's now regarded as the final version of general relativity, the correct form of the field equations. I should note, by the way, that I just said that, so Einstein's paper is November 25th. I just said that Hilbert submitted a paper November 19th. So there's a discussion for a while about whether Hilbert actually got there first. One thing to note is that Hilbert never claimed to have figured it out first, so he never staked a claim to priority. But historians have gone back to look at this more carefully. And it turns out that there's some interesting twists here. The sort of twists that when you're doing historical work and looking at archives sometimes come up. So the way that papers were published for Hilbert was that he read them probably from a manuscript or a typescript that he read to an academy. So that's when I say he published a paper on 19th. That's when he read it to the Göttingen Academy. The paper itself didn't appear in print and wasn't submitted to the publisher until several weeks later. I believe it was Leo Corey was the historian who went back to the archives and found the typescript of the original talk that was given on November 19th. Now there's a particular question. There's a few equations that would be quite revealing if they appeared in that typescript. It turns out that the typescript of what was probably the original lecture has a few chunks missing where there were parts that were cut out. Now this is actually not devious or anything. This is probably when you only have a typewriter or whatever equipment you're having then, you literally cut and paste things into papers. So the fact that the piece is cut up is not all that surprising. But it's actually not clear. So Hilbert has the final field equations in the later version that was submitted to the press, but it's actually not clear if you go back to what he would have read on November 19th, whether the crucial equations that would have established that he figured it out before Einstein are there. So sorry that it's not cleanly resolved, but there's evidence that he was still sharing in some of the confusions that Einstein had. So in that sense, I think the advantage, in my mind, goes with Einstein, but it isn't as clear-cut as you might like in terms of the documentary record. And as I say, Hilbert never claimed that he had priority in this discovery. He always gave full credit to Einstein. But in any case, we have then the culmination in this dramatic race over this last month, which Einstein, as I mentioned earlier, later described to a colleague as the most intense month of his life. where he was often forgetting to eat. He was working so hard, and he ended up finalizing the theory. Now let's come back to one of the questions that reflects on the theme I've been pursuing, namely, in what sense does this generalize relativity? In what sense does it fulfill some of the principles that Einstein used in guiding the search? So I think at this time, Einstein would have thought, again, so at this time, he was thinking of a generalized theory as something that satisfies this property of being generally covariant. And I think in 1915, he would have thought that if you have a generally covariant theory, it's the case that first, Mach's principle holds, namely that inertia is defined relative to other bodies rather than to space itself, right? So he thinks that that principle is just automatically holds in a theory of this form. And also that in a clear sense, relativity has been extended from inertial to arbitrary states of motion. So he thinks that he has effectively achieved the goal of extending relativity. But I think his satisfaction was short-lived in the sense that he soon discovers that both of these claims are in fact wrong. So he's come up with a final theory, a successful theory, but it doesn't reflect all the things that he thought the theory should do. And in particular, he enters into a correspondence with the Dutch astronomer Willem de Sitter, in which de Sitter gives a counterexample to Mach's principle. In other words, something that satisfies the theory that he's written down, but seems to go right against this formulation of Mach's principle. And in a different case, Erich Kretschmann argues that general covariance, this mathematical property, doesn't guarantee what Einstein thought it did, in part by arguing that Newtonian mechanics itself, it can be written in a generally covariant form. So it turns out that some of the things that Einstein thought his theory should do, or some of the properties he thought the theory should have, weren't in fact present. But nonetheless, so despite the failure to generalize relativity in this sense, Einstein successfully combined deep insights about the crucial features of gravitational theories with the new concepts of space and time and special relativity. And the one thing I haven't emphasized is that this set of guiding principles that Einstein used in trying to formulate the new theory was in interaction with a number of other constraints that were also quite important in these last 2 years, where Einstein was looking at other physical theories and trying to copy the sort of mathematical structure of those theories in order to produce his own theory. So although not all of the things Einstein desired along the rough and winding road were satisfied, he did realize deep conceptual points about the nature of gravity that are long-standing contributions and will probably still be realized in some sense in successor theories. And the philosophical exploration of the basic concepts was a large part of that achievement. And let me just mention finally, as I said before, about 4 years after this, is actually in November 1919, that Einstein gets the good news. This is his colleague, the Dutch physicist Lorentz, sends him news that Arthur Eddington's observations seem to confirm the light bending around the sun that his theory predicted. So this is the point where people started to say, okay, this is really strong evidence that Einstein's theory was on the right track, and this is where Einstein became an international celebrity essentially overnight. So he's on, his theory gets mentioned all over the place as a result of the Eddington eclipse expedition. Okay, so let me wrap up then by saying something briefly about what I see this as illustrating about the philosophical contributions to physics. So the characteristic approach that Einstein took to physical theories was to give a very incisive and careful treatment of what concepts are actually essential to the empirical success of those theories. What parts of the theories are really crucial? And we saw in 1905 that he argued that various common assumptions we have, or conventional wisdom about space and time, are actually not supported by the theories we have. And he gave an argument that those can be replaced with a very different conception of space and time that more accurately reflects the structure of the theories. And he also was able to recognize deep structural features that should guide formulation of new theories. And this is something we saw in his attempts to formulate a theory of gravity, he identified particular features of theories that he thought had to be preserved. And Galileo's treatment of free fall was one of those, and he thought that there had to be a connection between inertia and gravity that was acknowledged and had a particular place in the new theory. So I think these are both characteristically philosophical contributions to physics, and I'll close with that thought then. So thank you very much.